environment is a challenging task, especially when we have a limited scalability. And one of the most common strategies to tackle this task is model predictive control, MPC. However, MPC requires a global guidance to ensure effective navigation, especially when navigating beyond the line horizon or when we're having a changing environment. Most of the existing approach provides this global guidance by integrating MPC with either a global motion planner, which requires building a global map, or a data-driven approach, which requires an offline training phase. Different from the existing approach, we propose GP-MPPI, which is an online learning-based control strategy that integrates the model predictive path integral control MPPI with a local perception model based on the Sparse Gaussian Process. So the key idea here is to use the GP learning capability to teach the robot its surrounding navigable space, to identify the subgoals in the free navigable space, and to recommend one optimal subgoal for the MPPI. Where MPPI will compute the optimal control sequence, which satisfies both the robot and the collision avoidance constraints. This approach will eliminate the need for building a global map or having an offline training process. So our system has two main components, the GP subgoal recommender and the MPPI. MPPI is a sample-based model predictive control which can be applied to nonlinear dynamics with non-complex cost function. And simply the idea of MPPI to sample thousands of trajectories online from system dynamics, then evaluate each of them based on a predefined cost function, and then update the optimal control sequence for all the trajectories. The GP subgoal recommender is a local perception model where we transform the augmented cloud data into a spherical coordinate and project them into a circular surface around the robot known as the command surface. Then we use a Sparse Gaussian process to model the probability of occupancy over the surface. And as you can see here, the predicted occupancy from the SGP model is equivalent to the original occupancy surface. However, the uncertainty associated with the prediction of the SGP model constructs another surface called the variance surface, where the uncertain area of the prediction, shown here in the white colors, represent the navigable spaces around the robot. And we define the centroid of each navigable space as a GP frontier, which also can be a potential navigation subgoal. And from this GP frontiers, we select one based on a cost function, which will take into consideration both the distance and the direction of the GP frontiers with respect to the final mode. We introduced two operation modes for the GP-MPPI. The first one, the simple mode, where the MPPI always follows the GP recommended subgoal all the time, while in the recovery mode, MPPI only follows the GP recommended subgoal when the robot is at risk of getting stuck in a local minimum. And here you can see the simulation results of both the simple and the recovery mode in a simulated maze-like environment, where both methods are able to navigate the robot to the final goal without any collision, with velocity over 1 meter per second. And furthermore, we calculate the assisted percentage, which represents the portion of the trajectory where the MPPI needed help from the GP recommender to avoid getting stuck in a local minimum. And for this maze-like environment, the percentage was 42%. Finally, we validated our approach in an L-shaped corridor, filled with cluttered, different size, different shape obstacles. And here you can see that both the simple and the recovery mode were able to find a field collision path to navigate the robot to its final position. And here the assistant percentage of the GP to the MPPI is 25%. While as you can see in the right, both the baseline, the MPPI, and the local MPPI were stuck at a local minima just after the robot started to navigate. Thank you, and I'm happy to answer your question.